Okay, so let's go through the data for the lab where we are analyzing a silver copper alloy. So down at the bottom I've got the data. If you didn't pick up on anything from the videos, we had the mass of the original dime, which was the silver copper alloy, 1.3 grams. The mass of sodium chloride used, I used 1.4 grams. We're never going to use that number. That's what we calculated on the second video, I believe, where we did this first calculation. We needed to know the amount of sodium chloride needed to completely precipitate all the silver in the sample, assuming that the sample was 100% silver, which it was not. So I originally had 1.3 grams of alloy, which was a mixture of silver and copper, but for that first calculation, we assumed all silver. We wanted to do a little stoichiometry to figure out how much chlorine, specifically how much chlorine we need to completely precipitate all the silver as silver chloride. Well, the vehicle of getting the chlorine in the solution was sodium chloride. And the most important thing to know is that because sodium and chlorine and silver ions are all +1, -1. In this reaction, everything is a 1-to-1 ratio. When we get into chapter 4, we'll look more closely at different types of chemical reactions and balanced equations. But the gist of it is kind of this, that we have the silver ions +1. We're going to put them in a solution of sodium chloride. So remember those like aqueous, and these were aqueous ions. Aqueous means in solution. So we had these colorless silver ions in the solution. We took the sodium chloride, we dissolved it in water to make it aqueous, and then eventually it's kind of one of those replacement reactions where the sodium ions kind of switch place with the silver. And then one of your products will be the silver chloride. The sodium ions are aqueous. They eventually went down the drain. But the most important thing was this precipitate. When chlorine reacts with silver, you form an insoluble precipitate. And then that let me filter out the silver in the form of silver chloride. So assuming that the dime was all silver, we did a little stoichiometry to figure out how much sodium chloride we would need to completely react 1.3 grams of silver. And from there, the most important thing was to know that it was a 1-to-1 ratio. We calculated about 0.7 grams of sodium chloride, which was already excess chlorine, because that 1.3 gram sample was not all silver. Some of that was copper. But to ensure that without a doubt no silver ions are left behind unprecipitated, we doubled that 0.7 grams, and I used about 1.4 grams of sodium chloride. There is way, way extra, more than twice as much sodium chloride as we needed. But we really wanted to collect every silver ion. We had the little tiny filter paper. Then we took the mass of the filter paper and silver chloride precipitate now that it's dry. And then all you have to do is subtract off the filter paper to get 1.57 grams of silver chloride. All right, so then let's see what else we got to do here. No matter what, even if we were in class, everybody would have the same answer for number 2. Calculate the percent silver in silver chloride. I almost kind of wish that in here it would say calculate the theoretical, because that's what we're looking for. We want to know any sample of silver chloride is what percent silver by mass. So we're going to use our periodic table. We're going to use theoretical masses instead of lab data. So I want to know the percent silver in silver chloride. So the mass of silver on my periodic table is 107.87 grams. And then we just divide by the mass of silver plus chlorine. Silver plus chlorine, 143.87 32. We'll plug it in, we'll multiply by 100 to make it a percent. And because these numbers are not lab figures, like I did not measure any of these, when you're reporting a percent like this, you can just go 2 decimal spots. That's plenty of precision. That's going to leave me with about 75.27% silver. Everybody has the same data because any sample of silver chloride should theoretically be about 75% silver by mass. Which then means that 75% of this should be silver. So I collected about 1.57 grams of silver chloride, and about 75% of that should be silver, which is our next calculation. So I'm going to move this up a little bit. Number 3, calculate the mass of silver in the alloy. Now, according to the law of the law of conservation of mass, definite composition would have been the silver chloride. Any sample is about 75% silver by mass. But then there's this law of conservation of mass that says that in a chemical reaction, you cannot create and destroy mass, matter, atoms. So all of the silver from the original alloy should now be in my silver chloride precipitate. We just took the silver, we turned them into ions by reacting them with this nitric acid. Then when I added the chlorine from the sodium chloride, every last silver ion should have then become a silver chloride precipitate. That there should be no silver left behind, no silver in the flask, no silver down the drain. Hopefully it's all in my precipitate. And I know that of the precipitate, I'm going to use this as a decimal, 75.27% of that precipitate should be silver. So then I'm just going to multiply by the mass of my sample. 1.57 grams of silver chloride collected. Super easy. This is about 1.18 grams of silver then. But that's usually what throws people off a little bit in question 3. They're like, silver in the alloy, what? And they're confused as to why we're using this number instead of like the mass of the alloy. Well, because we don't know the percent silver in the alloy. That's the whole point of this. But we do know the theoretical percent silver in silver chloride. Now number 4 is where we can really calculate then the percent silver in the alloy. So now I know there was 1.18 grams of silver in the precipitate, the silver chloride, but it all came from the original alloy. So now we can divide by the mass of the alloy. That was 1.30 grams. Times 100 to make it a percent. We'll plug it in. And, let's see. These are lab figures, so maybe I'll go 3 sig figs. I'm going to say 90.8% silver. Now, I guess then to get the percent copper, we can just subtract from 100, right? And so then we'll say 9.2% copper by mass. Nice. Good practice. I should do this too. Obviously, whenever you're doing free response and you're showing your work, it's not a bad idea to circle your final answer or put a box around it, just in case your work ever gets a little bit crazy or you're erasing things. Then it's easy for the reader to know exactly what you mean for your final answer. Hey, this is not bad data, because guess what? These dimes that I used, they're called Roosevelt dimes. And theoretically, they were made to be, are you ready? 90% silver, 10% copper. No way! That's really good data. I'm patting myself on the back right now. I'm sure you would have done just as well, if not even better. That's fantastic. Okay, so that's kind of it for the heavy math, the heavy calculations. So a little bit of stoichiometry in the first question, but then some of this was just percent composition. Number 5, describe the silver chloride and the copper 2 chloride products. So when you submit your lab report, if it's easier to have written the calculations on paper, you can just submit a photo. You can just put the photo in the lab document of your calculations. But for some of these, if you want to just type your answer in the space provided, that's okay too. Or you can just write everything on paper and then just upload a photo of all your work. Either is fine. The silver chloride, that was the white precipitate. PPT is an abbreviation that you can use for precipitate. Now obviously when you submit your work, you're going to write a complete sentence. You're going to say, the silver chloride was a white precipitate. Or you could write PPT. You're going to write, the copper 2 chloride produced was a blue solution. The copper ions stayed in solution because they did not react with the chlorine. Copper chloride is aqueous. It stays in solution. It eventually dripped through the filter paper and I dumped it down the drain. And I think we kind of showed that in the end. If you look real closely at the flask, it still has a little bit of a blue tint to it. You can for sure see the blue copper ions when you first take the solution out of the fume hood. The silver ions are initially colorless, but copper solutions are traditionally kind of a blue color, blue or green. It's really pretty, but it's kind of a good way of identifying a copper solution. And they were still present at the end of the reaction. I mean, it's diluted because we added more water in the filtration process, but it's usually still got a little bit of a blue tint before we throw out that final solution. Number 6, why was a twofold excess of chlorine added to precipitate the silver? Which that kind of answers question 7 while I'm thinking about it. Number 7 says, was the silver or the chloride the limiting reactant? Well, they just tell us in number 6 that there was excess chlorine. So I guess by process of elimination, the silver was the limiting reactant. And I guess if I just finish number 7 while I'm thinking about it, why was silver the limiting reactant? But this is the ion we wanted to collect. We wanted to fully collect all silver ions. So if you know you want to get every last silver ion, then just add a little extra chlorine. I didn't want to take the chance that there'd be some poor little silver ions that didn't get to partner up with a chlorine. So we just added a boatload of chlorine. We wanted to study the silver. So we wanted to make sure we fully collected all the silver. Which again kind of goes back to number 6 then. Why was a twofold excess of chlorine added to precipitate the silver? It's kind of the same thing. I almost want to just write the same thing. Maybe I'll say like, we wanted to, oh my gosh, like my brain is saying that we just really wanted to make sure there was enough chlorine for every silver ion. I mean, really, 6 and 7 are kind of getting after the same thing, aren't they? And so often that's what we do in the lab. If there's one particle that we really want to study, we really want to collect, then we'll make sure that we just take the other one and put it in excess. Extra sodium ions or extra chlorine ions didn't affect my reaction. They're down the drain now. I really like 8. It gets a little bit into the next unit on reactions. Why is it possible to analyze the silver content in a silver-copper alloy by precipitating it with chlorine ions. So here's kind of the key, and maybe you remember this a little bit from last year, like when you learned about the single replacements, double replacements, or some people call them displacements. Either is fine. That there's like these solubility rules, that there are certain ion combinations that are soluble, and there are certain ion combinations that are insoluble, and they form precipitates. Chlorine was a great choice here because silver chloride is a solid precipitate, but the other product would have been copper chloride, but copper chloride is a solution. And so we call this selective precipitation, where we wanted to selectively precipitate only one of the ions. So you have to make sure that you pick a reagent, chlorine in this case, that will only form a precipitate with one of the two ions present. Aha! And so if I would have picked something like, for example, hydroxide would have precipitated both. Silver hydroxide and copper hydroxide would both be solids. And so then you would get this giant precipitate. It would collect on your filter paper, but it's got both the silver and the copper, so that does me no good. I only want one to be a precipitate so that I can separate them. One's a solid, one stays in solution. And the last few, if the silver chloride is not dried, which ours was dry, and you can't feel it, but I could feel the bottom of it, and it was definitely dry. When the mass was determined, will the calculated percent silver be too high or too low? Okay, so let's say we backtrack a little bit through our calculations. Here is the mass of silver chloride that we measured. Well, that's what we got when we subtracted off the original filter paper from the mass today of the silver chloride plus the precipitate, which is this guy. Mass of the filter paper plus the precipitate. But if that wouldn't have been dry, then really the mass we would have taken today would have been the filter paper, the precipitate, and excess water. So we would have subtracted off the filter paper, and we would have had this number right here then. But that would have technically been the mass of the silver chloride and the water. And so this 1.57 would be too high. Well, if the 1.57 is too high because it's got water in there, well, even then when I multiply by the percent silver, then this number is going to be too high, which then goes right here. So that number is too high, and it's going to make my percent silver too high. And so if I'm explaining that in 9, we could maybe say something about the mass of silver chloride. Obviously, first I could say it's going to be too high. That mass would be too high. Would be too high because it also contains massive excess water. Because it also contains mass of excess water. We assume that the mass was all silver chloride, and then that we are calculating the mass of just the silver. But that water mass is going to skew my data. It's going to seem as though the percent silver is too high, but it's just because I've got extra mass in there from water. And then finally, when we get to number 10, you can do this one on your own. This is just the exact same calculations, but with some different data, just to see if you really understand the process that we went through in getting the percent silver and copper. So here's somebody that did the exact same lab. They had a silver copper alloy. the mass of the original alloy sample was 0.1264 grams. When the alloy was dissolved in nitric acid, the silver was precipitated as silver chloride, and this time the mass of the silver chloride precipitate is 0.1375 grams. And from there, you can take those two numbers, run through the exact same set of calculations to get the percent silver and copper. So this one, feel free to kind of run through on your own. I'll give you a hint. I don't remember the exact numbers off the top of my head, but I think it's about 80% silver and about 20% copper. I'd have to run the numbers, but I think it's about 80-20. So if you're in the ballpark, you're doing good. And obviously, if you get really stuck, send me a note. Or you could even say, like, this is what I was thinking. Is this about right? I'm sure that you're on the right track. You're above average intelligence. Finally, then, we're going to write a paragraph, conclusion, describing our results, discussing our errors, how they affected our percent, and what could be done differently in the future. Okay, so just in general, when you write these conclusions, it's not meant to just be a laundry list of every possible error imaginable. It's got to be errors that describe your results. It's logical sources of error that explain my percentages. It's not meant to be just anything I could possibly think of. And so we have to also be kind of specific, and we can't just say, well, maybe we did the calculations wrong. Now, a few times that came up on the first lab, the hydrate lab, and I just kind of made some notes like, that's not really what we want on an AP style question. But I didn't really ding anyone for it on the first lab. But we're not going to do that on the second one. So we're not going to say that we did the calculations wrong. Don't submit your lab report if you did the calculations wrong. Or if you did the calculations and you're like, whoa, my data is whacked out. Well, then let me know before you submit it. You can't just say, well, I think I did it wrong. Do it right, or figure out what you did wrong. Kind of along the same lines, we're not just going to say, I think we measured wrong. We didn't measure wrong. We just put everything on the electronic balance. We didn't measure wrong. There's no error in our lab measurements. Now, if you think that you did make an error in your measurements, then you have to be specific and say, oh, I think I forgot to hit the 0 button when I took the mass of the filter paper, or something along those lines. Like, now that I look at my data, yeah, something's off with my mass of whatever. I would like to go back and mass that again because I think this is what I did wrong. Okay, now that's more specific. But we can't just put blanket statements in that are kind of generic. And on the AP free response questions, on the real test, there's always one that's kind of labby in nature. And they'll eventually ask you to analyze the data and describe logical sources of error. Or they might give you a source of error and say, would this error pertain to this data? Would this error be consistent with their results? And we would say yes or no and justify our answer. So we really have to understand the possible sources of error, but then how they would affect the data. So obviously, we're really good. But most of the time, you're either a little too high or a little too low. So this was supposed to be 90% silver and 10% copper. And now we didn't really study the copper. We collected the silver, and then we just got our percent copper by subtracting from 100%. So we're going to kind of focus most on the silver and the silver chloride that we collected. So it's supposed to be 90% silver. Now you could be under 90, or you could be over 90, which we were a little bit over 90%. Whoopsies, 90%. Now, obviously, that's where we're going to focus for our conclusion. But it's good to understand both sources of error, because what if you got a free response question and it walked you through these similar calculations, and then at the end they had data that was like 80% silver It was 85% silver. Is this a logical error? So we should kind of understand both sides of the story. Now ours was just slightly above, and I think it's because of the slight contamination. Obviously, it's impossible to collect more silver chloride than what we calculate, but if your percent is over 90, the silver chloride is contaminated. There's too much mass on the filter paper. So then we have to think, what are our possible contaminants? Well, I think ours was probably, oh gosh, I'm going to say like dirty filtration apparatus. And I think I kind of show you that in the video, because I could kind of see the next day once everything was dry that, I mean, the silver chloride is supposed to be white, and there were some little kind of dark gray speckles in there, and I think it's from that filtration apparatus that I didn't go in there and like clean it out real good before I used it, and maybe I should have, because then that's what we're also going to talk about in our conclusion. We're going to explain that our percent yield was a little bit too high. It should have been 90, or I should say our percent silver was a little too high. It should have been 90. Most likely then that means that our silver chloride was just ever so slightly contaminated. And because I did notice the dark specks, it's probably from the dirty filtration apparatus. So next time I would clean that out well before using. Oh. Now, another possibility would have been water, wet precipitate, but ours was not. So I'm going to say not ours, but that would be another logical error that would cause my percent to be too high, is that there's something else on the filter paper besides silver chloride. It could be water or some kind of a contaminant, in our case, from that filtration cup on top. Now, if we would have been under 90%, then we would have lost silver chloride during filtration. And so maybe that would have meant that we didn't wash out the beaker well enough. Didn't wash out the beaker. Now again, these are not things that we're going to talk about in our conclusion, but I'm going to put them down here in case you ever got a free response question on a test or a quiz that gave you data similar, but the yield was less than we expect. Well, then somehow we lost product. And so when we're filtering, and maybe you remember from last year, you got to add extra distilled water. You got to make sure that you completely rinse out your beaker. We got to make sure that we don't lose some of the precipitate off the filter paper. So maybe some precipitate fell off the filter paper. That happens. I mean, sometimes it's hard to get that little filter paper out of the funnel, and so you might lose a little bit. That's like, oh man, it's still in the funnel. Or maybe it's on like a paper towel and you bump it, and some of the precipitate like falls onto the lab table or something like that. Oh, I just thought of something really good, and then I think we're done. Here's another one that we could put in our section. Not washing the precipitate. Ooh, this is a good one. So our best ones are going to be this one and this one. So when you filter and you get all done, you're supposed to rinse your precipitate with distilled water, which I did. I did it once. I just squirt some distilled water in there and just kind of rinse it. I think often first year chem kids think that if there's ever a clear, colorless liquid, it's water. And that is so not the situation. That when we had that flask, ooh, that's not a bad flask. And so I collected, like here's the filtration apparatus on top. And that's where I collected my precipitate. And then drip, drip, drip. This liquid dripped down into the flask, which we eventually threw in the garbage. But that's not all water. That liquid that was dripping through was a combination of a whole bunch of things. Number one, it's sodium ions, it's excess chlorine ions, it's the copper ions, it's extra nitric acid from the first day. It's not water. I mean, there's water in it, but there's all kinds of junk in there. And all that junk will collect on my filter paper and add mass. So good filtration technique is that once you're done and all the liquid drips through, you should really rinse it a couple times with some distilled water to make sure that none of those other ions are collecting along with my precipitate. So I washed it once, but if I could do this lab again, maybe I should have washed it 2 or 3 times with a little extra distilled water. All right, there we have it. So all you have to do then is either submit photos of your work into that document in Canvas, or some of this, if you prefer, feel free to type right in there and then hit submit.